Ladies and gentlemen, good morning. Today, I'd like to talk about the numerical model of the high-speed wear and real adhesion and starved interfacial contaminations with surface roughness. I'm Ming from Suzhou University. Now, I'd like to lay my stress on the following 4 parts. Now, let's start with the introduction. As we know, the railway transportation is developing towards high-speed, heavy haul. It needs larger adhesion force for the traction and braking. However, the railway system is an open system. There are many contaminations. All these contaminations may cause low adhesion, then cause wear-real damages such as scratch and spotting. It's very dangerous for the running safety. Therefore, it's important to clarify the mechanism for the adhesion, especially contaminated by all these contaminators. Many researchers have done a lot of work on wear-real adhesion. There are many 2 parts. They are experimental studies and numerical studies. As to experimental studies, there are many focus on the interfacial contamination is dry, water, oil, sand, leaf, water and oil mixture, and so on. In the previous presentations, leaf had been investigated by many authors here. Compared with experimental studies, there were less studies on numerical studies. Here, there are only mainly 2 models on the numerical studies. There are a stochastic model and a deterministic model. Here, in the presentation, we based on the stochastic model and extend this model to consider more factors. Although many researches had been done, however, new numerical model by now can take the effect of starvation and elastic behavior into one model. Here, this presentation will deal with it. Now let's go through the numerical simulation model. It contains 2 models, sub-models. The first one is contact model. Here, I just describe the difference between the flooded case and the starved case. There are mainly 3 differences. The first one is the contact area. Here, we divided the lubrication area into 3 parts. The first part is a flooded area, that is contact range. In this range, the hydrodynamic pressure can be built up. The second is there are 2 cavitation areas near the inlet and the outlet ranges. In these areas, the hydrodynamic pressure cannot be built up. Secondly, here we introduce a parameter, the thickness of supply of layer, H oil, as an input to my models. It can define the level of starvation station. In addition, the position of the areas mentioned above are not known before. They can be solved during the numerical procedure. Here, in the previous studies, we use ZMC or GG empirical equations to simulate aspirated contact. Here, based on the field test of wear and real surface roughness profiles, we developed a FEM model and do a lot of simulations. And based on the simulation results, we fit the aspirated contact pressure by ourselves. The second model is the temperature model. This figure shows the calculation done for the temperature. It contains three parts. There are the temperature inside the wheel and the reel and across the film thickness. Now let's look at the numerical procedure. It contains two fields. The first is the pressure field. Since the starvation condition had been taken into consideration, so the classical average Reynolds equation should be modified by introducing a parameter, fraction film thickness. The work done by, based on the work done by JFE. Here, theta is defined as the ratio between H oil and film thickness gap H. The following boundary conditions should be added into the numerical procedure. Here, these equations are the aspirated conductor pressure equations based on the FEM results. Then we compared the present empirical equations to the classical models such as KE and JG. From these results, we can find that the present model agrees well with the JG model. The JG model is recognized as the most accurate aspirated contact model. So this, the present model can simulate aspirated contact very accurate. Then, by the procedure, we can get the convergent pressure field and use this field as the initial condition for the iteration of temperature field. Then we can also get the convergent temperature field. Then use this as the new initial condition for the pressure field iteration. That is to say, these two fields will be iterated with each other. Now let's move to the third part, results and discussions. In order to obtain the contact characteristics, the parameters used in our model are listed in this table. As mentioned above, the matching method and multi-level method are used in our model. So the information for these two methods are listed as follows. Now, firstly, we obtain the pressure field under oil contaminations. Figure H is the description of liquid pressure. It has four characteristics. The first is the spike here. The spike of liquid pressure vanishes when H oil is less than 3 micrometers. And no obvious cavitation area is found in the inlet region when the inlet oil layer, that is H oil, is larger than 8 micrometers. In addition, the cavitation boundary is getting closer to contact zone with the decline of H oil. The position of the cavitation boundary is related to the abrupt change of the gradient of liquid pressure. Figure B shows the distribution of fraction of film thickness content. It also has the following characteristics. Here I describe it in brief. There are two cavitation areas in the inlet and outlet region, and with the decline of H oil, the cavitation becomes close to the border of the Hertz contact zone. That is similar to figure A here. Here, theta gradually improves from the constant inlet oil supply and has a jump here, to unit where the pressure starts to build up. This is quite different. This is quite different from the flooded case. Fig C and Fig D are the descriptions of film thickness and asperated contact pressure. They have the reflection relationship with each other. From Fig C, we can see that it's quite different from the flooded case. It has jump point. Here, jump point. The position of the jump point related to the cavitation border. In Fig A, Fig B, we can find the position of the jump point. Before the jump point, the H oil is equal to the film thickness is equal to the H oil, and after the jump point, it equal to the flooded case. Okay. Now, this figure shows the temperature field under oil contaminations. It can be concluded as the following conclusions. The important one is that the spike of the temperature increases with the increased oil. We can find here, here, and there. This figure discusses the effect of Chen speed. From this figure, we can find that the adhesion coefficient decreases with the Chen speed, under both and starved intervention contaminations. And starvation has less effect on adhesion coefficient under wet conditions. And the adhesion on the oil-starved contamination is larger than that under the flooded contamination. At last, we investigate the effect of inlet film thickness H oil with various surface roughness. From this figure, we can find that an interesting finding. With the increase of H oil up to 4 micrometers, the asperated contact force decreases. When H oil is larger than 4 micrometers, the asperated force have a slight increase. That is very interesting. From this figure, we also can find that the roughness also has a significant effect on the asperated contact force. The rougher the surface is, the larger the asperated contact force is. Now, I'd like to conclude my presentation as the following 4 parts. The first one is that as to the oil contamination, when the inlet oil layer thickness is down to 1.9 micrometers, the inlet region is completely the cavitation area. Secondly, the boundary of the inlet cavitation area are controlled by the inlet oil layer, that is H oil, both oil and water, starved cases. Thirdly, the well and real adhesion coefficients decreases with the increasing running speed, both flooded and starved conditions. The last one is that with the increase of inlet film thickness up to H oil equal to 4 micrometers, the asperated contact forces decreases. When H oil is larger than 4 micrometers, the asperated force have a slight increase. That is my presentation. Thank you for your attention.